Okay, this is part 2. We worked out the bugs. We got the resistor values. And if you didn't see part 1, I'll link that below in the description. But as far as this goes, it's basically using the MM5314N with the 74C915 with the CD4028. Instead of having a 7-segment output, we're going to have a 1 of 10 output for driving edge-lit displays and similar. So basically the problems I had in the beginning trying to get BCD working out of this 74C915 needed pull-down resistors on every one of the segment lines. So A, B, C, D, E, F, G, 100K to ground. That squared off the bottom of the waveform and allowed this chip to actually work properly. As soon as I did that, with a little tip from a friend of mine, instant BCD outputs working. And then I had problems with implementing, well, not implementing, but getting the LEDs to work properly. I did not have a base resistor on the 10 transistors. I added a 2.2 k ohm in there, and that made all the difference in the world. Let's see, what else did we do here? This is your AC reference. Comes in. That's what the chip uses to keep time. Multiplex. RC network here. Initially I did have 100K here. I put a 220 in instead to bring the frequency down. It was pretty high, so most of the clocks I work on are 800 to 1500 kilohertz in the frequency range. That's the scan rate between the 6 digits, which is controlled by these 6 transistors down here. So seconds through hours, sequentially scans. And that's how that works. What else do we do here? So these LEDs, the 10 LEDs as I discussed earlier, but ones of seconds, ones of minutes, ones of hours have 10, tens of seconds, tens of minutes have 6, and tens of hours have 3. We got a digit 2 in case we want to do 24-hour time. Alright. So in case the other schematic was a little difficult to read as far as the LEDs go, this is what the circuit's intended to drive. This is the 1 out of 10 multiplex LED configuration. So for seconds we're going to have 10 LEDs, alright, 0 through 9. Tens of seconds, 6 LEDs. Minutes, 10 LEDs. Tens of minutes, 6 LEDs. Hours, 10 LEDs. And tens of hours, 3 LEDs. Alright. So, and all the anodes are common together and brought down to the, they're going to be controlled by the digit drivers. There's 6 transistors that do that. So you got your tens of hours, ones of hours, tens of minutes, ones of minutes, tens of seconds, ones of seconds. Main current limiting for the LEDs, I use 220 ohms in the return circuit before the transistor, which completes the path to ground. Keep that in mind. Up here I had initially in the design a variable pot with the idea of dimming the display. Well, that didn't really work out because the base current through the transistor was still enough to keep the LEDs on. So I couldn't really dim enough, so it wasn't really worthwhile putting that in there. Although extra current limiting I found after operation of the clock or the circuit is needed. So I had already installed these 220s down here. So instead of the variable pot, I ended up putting a 330 ohm resistor in from the supply, which with the 9 volt AC adapter is running about 14 volts filtered and rectified. So this from the supply feeds the collector of all 10 transistors operating the LEDs. So total current limiting is the 220 plus the 330. The next build, probably consolidate them down here, 6 of them. You know, maybe play around with something around 500 to 600 ohms. Just be aware of that. Okay. I did add this little feature for blink and call, and I pulled off the A BCD line through resistor to the base of a transistor. Okay, and we have our blink and calling. It ends up at a half hertz, not a 1 hertz blink, but it's unique. I like it, so that's what I'm doing. Works good. Okay, so using a 9 volt AC wall adapter, rectified, filtered, we end up with about 13 volts, which is perfect. AC in, this is just a bridge rectifier, nothing fancy there. You tap for your 60 hertz reference right over where the AC comes in, and condition it and provide it to pin 16. Okay, another thing, the hold slow and fast, pins 13, 14, 15. To activate them, you're going to bring them low. Alright, so if they're left not connected, they're not going to be activated. So basically, through a switch, you bring them low at the same potential as pin 2. Okay, same goes for the 50, 60 hertz selection. This chip will actually run on 50 hertz for those people that have that need. Here I'm going to ground that pin so it runs at 60 hertz. That's the same potential as, again, pin 2. And the 12-24 hour switch, I actually did not ground this. I ran this to a switch. Alright, so if you leave this open, I believe, yes, it's 24 hours, right? So if you ground it, which I typically do, it would be 12 hours. So if you actually interrupt that ground connection, which I did, and run it through a switch, so it brings it to the same potential as pin 2, you can switch on and off the 12-24 hour function there. Alright. Okay, 2 more things before I forget. 4 or 6 digit select at pin 24. I grounded it here because we want 6 digits to operate. If you leave it open, it's 4 digits. And one last thing, not used here, but some applications actually use it. Output enable. If you leave that not connected, otherwise open, all the displays operate normally. If you ground that pin, it kills the operation of the displays. That pretty much covers all the functions of the MM5314N by National Semiconductor. Okay, let's do a little probing while the circuit's in action. Okay, pin 16, AC reference. That's the 60 hertz in. That's what's going to set the time base. The chip uses for reference to keep time. 12, 13 volts there. Above ground. And what do we got going on here? Let's see. There's our 60 hertz. That's the multiplex signal, pin 23. I think it's about 3.5 volts or something. Frequency 1.234 kilohertz. That's the scan rate now, between the 6 digits. Okay, upper waveform. That's the multiplex signal. That low part in that waveform is actually ones of seconds output. The other 5 are high. Alright. And so we're going to turn on the lower waveform here. And that's a segment output. This particular one is the A segment that I have connected to. And anytime that lower waveform lines up with the low spot in the upper waveform, that's actually the correct data at that time, and that'll transfer through to your ones of second display, right? So then you have other parts, you know, your tens of seconds, ones of minutes, tens of minutes. Okay, working, completed, ready to go, wired in. You'll have to see the video on the clock. That's a separate video, but this is the circuit. I installed the new 5314 that I had. The other one I was using just for prototyping, just in case I bridged something or screwed it up. I don't want to damage a good one, so it is now tested and working, and we have our set buttons: fast, slow, hold. We got a dimming pot, and I don't normally do this, 24-hour option. And there you have it. Hope you enjoyed.